Okay, so hopefully everyone can see me and hear me. Today we'll be talking about linear regression. So this is basically going to be part one of a two-part lecture on linear regression. Today I'll go over the, let's say, theoretical or conceptual basis of linear regression, and then I'll follow this up with more of a hands-on type of lecture where I'll do examples of linear regression by hand using the whiteboard app. We'll also do a synchronous session soon so that we're able to go through linear regression as a class, and that I could answer questions in real time. But let's first get some of this conceptual stuff out of the way. Now, I'm going to assume, hopefully, I'm right by assuming this, that you have already gone through the review for correlation. That's going to be very helpful in terms of helping to understand linear regression. Let me just resize this quickly. Okay, hopefully that'll be better. Let's see. Okay, so when we talk about linear regression, we'll first talk about understanding what regression actually is. We'll talk about the difference between predictor and criterion variables. We'll take a look about how we can use z-scores to make predictions. We'll also talk about raw score prediction. That'll make more sense, hopefully, as we go through this lecture. We'll talk about the regression line, or the line of best fit. It's a concept that we've spoken about. We'll go into much more detail in terms of that concept for this lecture. We'll also talk about error that exists in predictions when using linear regression, and then we'll also talk about multiple regression when we're using multiple variables to predict a single criterion or outcome variable. Okay, so getting straight to it, understanding regression. So we can remember that in a relationship, in a correlation, let's say, a particular x scores and particular y scores are paired. So for every x score, there's a y score. Therefore, if we know an individual's x score and we know the relationship between x and y, we know the strength and we know the direction, then we're able to make predictions about what that individual's y score might be. So hang on to that, or let's think about that for a second, right? So if we know that two variables are very strongly positively correlated, and you tell me someone scores low on x, then I can assume that they're also scoring low on y. How can I make that prediction? Well, because I know that it's a very strong positive correlation. So if they were scoring low on x, they should be scoring low on y. If they're scoring high on y, or x rather, then they should be scoring high on y, right? So knowing this relationship, the strength and the direction, can help us make predictions. So linear regression is the statistical procedure that is used to make these kinds of predictions. Essentially, we're making predictions of y, or y-score predictions, based on what we know about, number one, the individual's x score, and what we know about the relationship between x and y. So linear regression, again, is used to predict an unknown y-score, or predict unknown y-scores based on known x scores. So we'll see exactly how this works, but it operates on the principle of drawing what we call the linear regression line, also known as the line of best fit. through a scatter plot, essentially. So let's take a look at that again. We saw a bit of how this works with correlation, but we didn't really get into the details of it. So let's see how it works, and we'll start getting into some of the details. So we'll see that the regression line is a straight line. You only get one line to account for all of your data that exists in the scatter plot. So some scores are going to be closer to that line than others, and some scores are going to be really far away from that line. But the idea is that that line should best represent all of your data. So the line will do a good job at representing some data and probably do a bad job at representing other data. So as we'll see, that the regression line is a straight line. On average, it will pass through the center of your X scores and each of your Y scores, right? So let's go with our scatter plot that we saw in the example that we used when reviewing correlation. We said that this person here was an outlier, right? In this example, we're taking a look at the number of hours somebody studied and the score that they got on an exam. It's like a pretty consistent, pretty strong relationship between X, the number of hours you study, and how well you do on an exam. Again, except for this score, acting as an outlier. So we only get one line, one straight line to best represent all of this data. Now, I just eyeballed it when I was putting this line in there. There's no mathematics behind this. We shouldn't trust this line. It's for illustrative purposes only. But this line is the line of best fit, and it could also be referred to as the regression line. Okay, so let's keep that in mind. We're already familiar with the idea of the line of best fit, so we can now think of the line of best fit as also being a regression line, a line that we can use to make predictions. If you give me an X score, let's say if I have a line that best fits all of my data, or best fits the relationship between my X scores and my Y scores, and you give me a score of X, you say a student studied 5 hours, right? You give me a score of 5 on my X variable. They studied 5 hours. If this line is good, right? If it has low error in there, I should be able to say, well, I don't have any corresponding Y scores. I don't know what their exam would be, what their exam grade would be, but I can make a prediction. And I can do that by going up to my regression line, right? And then go over and say, yeah, given an X of 5 that they studied 5 hours, I'd predict about an 85 that that's what they would get on their exam. That's essentially, in a nutshell, how linear regression works, using this line to make predictions. Enter in any X score, go up to the line, move over, see what the Y score is going to be. It's a simplified version, but if it helps you understand what's going on, that's essentially what's going on. So we'll use the following symbols to distinguish participants' actual scores from the scores that we predict for them. So their actual score is just going to be Y. So no surprise here. This is, as usual, Y stands for the participant's actual Y score. But when we make predicted scores, we have to let people know that we're not talking about actual scores, we're talking about predicted scores. And there's two ways that we can do it, or two ways that it's done. So predicted Y scores are either displayed as Y with this little apostrophe here, and that's called Y prime, or predicted Y scores are displayed as y with this little symbol on the top that looks like a hat. And that's actually what it's called, believe it or not. It's called y hat, right? So whenever we're talking about predicted y-scores, not actual y-scores, but predicted y-scores, you need to refer to them as such. This way people understand that they are predicted scores, not actual scores. So also for samples of y-scores, when we're talking about, say, a group of y-scores, we'll discuss the mean of that group of y-scores as y bar, right? So typically we see x bar, because we usually deal with the mean for x scores, but here we're dealing with the mean for y scores. Also, sample variance will just have a y next to it, so we know that we're talking about the sample variance of the y scores, and the standard deviation also will have a y next to it, so we know that we're talking about the standard deviation of the y scores, right? So we use, compute, and interpret these terms the same way as before. So just standard formula for calculating the mean, standard formula for calculating standard deviation, but we'll be using y scores instead of x scores. So nothing too outrageous there. Some important assumptions when using regression. The first is that we are dealing with a continuous criterion variable. So what is a criterion variable? Criterion variable is the variable that we are trying to predict. So if I'm using GPA, or let's say I'm using a student's SAT scores to predict their college GPA, the criterion variable would be the college GPA. The predictor variable would be the SAT scores. So a criterion variable is what it is that we are trying to predict. And in linear regression, that variable, that criterion variable, must be a continuous variable. It can't be a categorical variable or a rank order variable. It must be continuous. Also, another assumption with regression, kind of see it in the name when we talk about linear regression, is linearity, meaning that the relationship between x and y is linear in nature. So it doesn't start taking on a different shape once we reach a point, right? It doesn't turn into a quadratic or a cubic type of relationship. It's a linear, straight relationship all the way through. We also have the assumption of normality, meaning we assume that y scores at each of the x scores are approximately normally distributed. So essentially that we're dealing with data on x and y that are normally distributed. Number 4, that there is little or no multi-collinearity. So what does this mean? Collinearity is when we have variables that are highly correlated with one another. This causes a problem with regression, because regression is going to want to treat, if you have two predictor variables, once we get into multiple regression, if you put in two predictors that are very closely correlated or very highly correlated, the regression model is going to want to treat them as the same variable. So your predictors should be different enough from each other that it's not going to screw up the model. If there's a lot of multi-collinearity, then the regression model again is going to say, yeah, those two variables are the same variable, and it's going to want to get rid of one of them. So your predictors can be related. They usually are related, but they shouldn't be strongly related, or it could cause some problems. Also, this issue of homoscedasticity. So what the hell does that mean, right? This might be the first time that you have heard this term. Well, it refers to the way that y-scores are spread out. More specifically, that the y-scores are spread out to the same degree at every x-score. The best way is just to show you an example of homoscedasticity. So, a model, a scatter plot that is homoscedastic would look like this. So each of these y-scores, right, they're spread out about the same at every x-score. You know, there's about the same variation, same variance going on in there. They're all kind of spread out equally across the x and y axis. A heteroscedastic distribution might look something like that. So we definitely want to avoid this. This would cause us some problems. Why? Well, because our regression line is, if we only had one line that we put through all of this data, it might go straight through this data, and the line is going to be more accurate down here. When you make predictions, these data points will be closer to that single line. But what happens when you move up on the x-axis? Well, the error is going to increase. The error rate of your regression line is going to increase. So we want our distributions to be, or our scatter plots rather, to be homoscedastic, right? We want nice, even, consistent differences here. We don't want to see something like this happen in our scatter plots. Okay, so we spoke a little bit about predictor and criterion variables, but let's just do a recap here. So the emphasis on prediction in linear regression leads to these two important terms: predictor variable and criterion variable. So a predictor variable refers to the variable that is used to predict scores on another variable. It's often your x variable, right? So x is your predictor variable, whatever it might be. And what is x trying to predict? It's trying to predict your criterion variable, which is also your y variable, right? So the criterion variable refers to the variable for which scores are being predicted. So we're using predictor variables. If we're doing multiple regression, we're using multiple predictors, but we'll start off simple with just one predictor variable that is trying to predict the criterion variable. So we'll start off with one predictor variable x, one x variable that we're going to use to try to predict the score on a y variable. Okay, so x predicts y is essentially what it comes down to, or the predictor predicts the criterion variable, or the predictors, plural, will predict the criterion variable. Okay, so prediction using z-scores. So when we talk about the prediction model, to make predictions with z-scores is that a person's predicted z-score on the criterion variable, meaning their standardized score. So it could be any variable that we're talking about, say somebody's height or weight or GPA or SAT scores or whatever it might be. When we're talking about z-scores, we're talking about this variable has been standardized, right? So they've been, whatever those initial values were, if they were height or weight or GPA or whatever, they've been converted into z-scores, right? So a person's predicted z-scores on the criterion variable, on that y variable, is found by multiplying a particular number called the standardized regression coefficient by the person's z-score on their predictor variable or their x variable. Okay, let's just take a breath there and see what this means. Predicting or prediction using z-scores means that I've already taken x and y and I've converted them, I've standardized them. So I've converted all of my x scores into z scores, all of my y scores into z scores, right? So I have a bunch of pairs of standardized scores. Z of x and z of y for the first participant, z of x, z of y for the second participant, so on and so forth. If we're going to try to make predictions about a standardized, say, y-score, a criterion variable, we want to know what's the standardized score for this person if they had a standardized x-score of this. Well, we would just multiply that standardized x-score by some regression coefficient, but it's a standardized regression coefficient. It's often referred to as a beta weight. We'll see what that means in a moment, or a little later on in the lecture, but also once we get to SPSS. SPSS, we usually, when we're running linear regression, we're using the standardized coefficients. They're just easier to understand. Okay, but we're taking a standardized z-score, multiplying it by some standardized, well, there we go. I forgot I had a formula here. So if we're trying to predict the standardized, and remember this has a little hat on it because it's a predicted score. If we're trying to predict what somebody's standardized score would be on y, we would take their standardized z-score, we would multiply it by the standardized regression coefficient, also known as beta, and we would get a standardized z-score out of that. Okay, so we're going to revisit this because, again, in SPSS we are typically more interested in the standardized scores. We're more interested in the beta weights here. They're just easier to understand when you're using multiple predictors that are all measured on different scales. Standardization does what the name suggests. It standardizes everything. It turns apples and oranges into peaches, right? So you can compare a peach to a peach instead of an apple to an orange there. Okay, so just to recap, in this formula, the predicted standardized z-score is the predicted value of the person's predicted z on the criterion variable of y. So the hat symbol there represents that this is a predicted value, right? Beta, this score here, is the standardized regression coefficient. We'll see how that's calculated in a moment. Z x is the person's z-score on their x variable, on the predictor of x, right? So again, this might seem more complicated than it is because we're working with standardized scores. If these were, say, raw scores, you could just think of, okay, we're going to take somebody's x score, their score on x, multiply it by some value beta, and we'll get a predicted score on the y variable. That's kind of easier to understand, right? Except now it's, instead of entering a participant's x value, we're going to enter in the standardized value for x, their z-score of x, multiply it by some coefficient called beta, and we're going to get a z-score or a standardized predicted score of their y variable. We'll see how this works out. It might take a couple times to fully understand how this stuff is how the stuff works. But we have the formula here. So a predicted standardized y score is simply our standardized x score times a standardized regression coefficient, or beta, right? So let's say, for example, at a college, the standardized regression coefficient is 0.25 for predicting GPA at graduation from SAT scores at admission. So the standardized regression coefficient between SAT scores when you're admitted and your GPA at graduation is 0.25. So a person who is applying to this school and they have a SAT score, standardized SAT score, of 1.5, right? So this means they're 1.5 standard deviations above the mean when it comes to their SAT score. They would have, if we enter in that number into our formula here, right? Their SAT score, standardized SAT score, is a z of x equals 1.5. So that would go here. We know the regression coefficient between these two variables is 0.25, so that would go right there for the beta weight. And we just do the math, multiply those two. So we would see that a person who enters the college with a standardized SAT score of 1.5 should graduate with a GPA, standardized GPA of 0.38, right? Or 0.38 standard deviations above the mean. Okay, that's not even half the standard deviation, so it's not that impressive, right? But it's showing that, okay, SAT scores might have some value in terms of predicting GPA, even though, you know, it's saying, well, there'll be 0.38 standard deviations above the mean. So how exactly do we calculate that standardized regression coefficient? That's what we're really interested in, right? We know how to calculate z-scores, so we can calculate standardized scores for x and standardized scores for y, but what about this standardized regression coefficient? How do we do that? Well, in bivariate correlation, so remember when I said hopefully you reviewed the correlation lecture and readings before viewing this, because regression is essentially a continuation of correlation. So when we are running bivariate correlation using z-scores, so when we're calculating the correlation using our standardized scores for x and y, then the standardized regression coefficient is simply r. It's just the correlation that exists between x and y. So if you're able to calculate the correlation coefficient between x and y, and you're using z-scores to calculate that correlation there, that's your regression coefficient. That's beta. That's the value you need right there. So pretty easy, right? So remember, when we're dealing with bivariate correlation and linear regression, your beta weight, the standardized coefficient, regression coefficient, will simply be r, the correlation coefficient that exists between the standardized scores of x and y. Okay, when it comes to raw score predictions here, so let's say in practice, if we're going to make predictions for many different people, say individual type of people, instead of as a group, trying to understand if somebody with this score came in, what would their the score on their x variable or predictor, what would their predicted y score be? If we want to make individual predictions, let's say, or predicted scores for individuals, we might want to use a raw score prediction model rather than a standardized score or standardized prediction model. So when we talk about raw scores, we're not dealing with z-scores. We're dealing with their actual values of their predictor variable, their actual score on x, and we'll get a predicted score on y. Not a predicted standardized score, but just a predicted raw score on y. So the raw score prediction model allows us to plug in a person's raw score on the predictor, which is x, and solve directly without using z-scores, without standardizing anything, to get that person's predicted raw score on y, the criterion variable. So to make these raw score predictions, we start with a number called the regression constant. It's called A. So when we see this formula for the regression line, A is the regression constant. So we start with this number, the regression constant A, and add it to the result of multiplying a raw score coefficient that we call B by the person's raw score on the predictor variable of x. That sounds like a whole bunch of mumbo jumbo. Let me show you what the formula looks like here, right? And those of you who remember, who from high school math, and didn't totally block it all out, this is the formula for a straight line, and that's what we use. That is the formula for a regression model. It's just the formula for a straight line, using one predictor here. We'll see once we get to multiple regression, we'll have x1 and x2 and so on and so forth. But just let's say I have an x score, and I want to predict what somebody's y score would be. Okay, well, we're going to multiply that x score by some regression or raw score coefficient, and then we're going to add the constant for it, and that'll give us a predicted y score. But let's take a look exactly what A and B really are here, right? Well, we know y hat in this case is the predicted y score. We see A is the regression constant in this case. B is the raw score coefficient in this case. And X is the raw score on the predictor. Okay, so we've broken down this whole formula. Let's see how it goes here. So as we can see, the formula for the regression line is just the formula for the straight line, where A is the y-intercept and B is the slope. So hopefully those terms are ringing a bell without sending you into a panic attack there. But we'll take a look. What do we mean by y-intercept and what do we mean by slope? Well, let's take some data here. Or we'll take a look at some different lines here. So the y-intercept is the point on the y-axis by which the regression line passes over, right? So at what point on the y-axis does this straight line pass? At what point does it cross over the y-axis? So let's take a look at this line, for example, this regression line or line of best fit. Well, it looks like it's crossing over the y-axis at 2, at the score of 2, right? Well, what about this line? Well, that line also looks like it's crossing over at 2, right? It looks like where it intercepts the y-axis is at 2. That line looks like it's crossing over at 2 as well, right? So in all of these examples, in all 3 of these lines, they all have the same y-intercept, or the same value for a, and that is 2. So the y-intercept is where the line crosses over the y-axis, right? Okay, so you see though that the angle at which these lines are drawn are quite different, right? This one looks more like a 45-degree angle. This looks lower, looks like a higher. So basically, they're taking on different slopes, right? The slopes of all these lines are different, even though their y-intercept is the same, right? They all cross over at 2, a y-score of 2, but their slopes are different. Their angles are different. So when we talk about slope, we're referring to the steepness and the direction of a regression line. So we could start just with an example here. In this case, we have a line that's crossing over, or a line with a y-intercept or an a value of 5. Here we add another line. It's a parallel line. It's the same slope, it's the same steepness as the first line, but that line's crossing over the y-axis at 3, so it has a different intercept, right? It has a different a value there. And finally, we have another line that has the same slope. It's not changing at all, right? These are 3 parallel lines. They have the same steepness, the same slope, but they all have different y-intercepts at this point. So their b values will all be the same for these lines, even though their a values are going to be different. Okay, so hopefully by visualizing what the y-intercept does, or what it looks like, and visualizing what slope looks like, hopefully this gives you a better idea of what those a and b values actually are doing. So when it comes to how to find a and how to find b, so how do we calculate the y-intercept for a raw score prediction, and how do we calculate slope for a raw score prediction? Well, I'll show you how to do it, but I don't want you to worry too much about how to do it, because by and large we're going to get this information using SPSS, but you should probably see at least how it's done. So how do we calculate the y-intercept and slope? Well, to calculate a, the y-intercept, you first have to calculate b. So the formula for b is actually not that bad right there. It looks, looks kind of bad. You might say, hey, Brown, that looks like a mess in there. It's actually not too bad though when you break it down. We're talking about the sum of some cross products, right? And the sum of x times the sum of y, sum of x squared, and then the sum of x squared. So these are things we're familiar with. We had to do them in 221, right? When we were calculating standard deviations by hand, and when we were calculating correlation by hand. So we're used to this. This shouldn't be too shocking, right? Now I know 221 tends to not make its way, or most of it doesn't make its way into long-term memory, so this might be relearning process for many of you, but we know that relearning something is easier than learning it. So it's easier the second time around. So let's do it. So we have our formula for B, and once we're able to go through this, we calculate B, then we're able to calculate A. And if you see that the formula to calculate A, the y-intercept, is a lot less work, right? It's simply the mean of your y-scores minus B times the mean of your x-scores. Problem is, you gotta calculate B in order to get A. But let's see how this is done. Let's do an example of this. So we have a data set here. We got some SAT scores, which are serving as a predictor variable, our x score, or x variable rather. Can't talk today. And then we have their corresponding GPA, or y scores, which are acting as a criterion variable. So we want to use SAT scores to predict y scores. How do we do this? Well, we're going to use the formula for a straight line, but we first need to calculate slope and calculate our y-intercept before we can use that formula. So we know that before we can calculate the y-intercept, we have to figure out what B is. We have to calculate B. So there's the formula for B. N is pretty easy. There's only 5 scores there, right? So we got that. That one's easy. The sum of x, y. So we'll create a new column and we'll multiply all the x scores by their corresponding y scores. And then we add them up. We sum them, right? So took care of that for you. Right? All I did is multiply 1000 by 3.3, went down the list, and added them up. So I got that value. Okay, we're making some progress here. The sum of x, all we have to do is add up our x scores. There it is, 5,380. Plop that there. So now we're almost done with the whole numerator of this formula. So we also now need the sum of y. Again, add them up, right? And we end up with 16.8. Boom. Okay, we're onto something here. We already know n is 5, right? So the next term that we need is the sum of x squared. Well, we already calculated. We didn't calculate the sum of x, right? We're actually going to have to come up with a new column, and we're going to have to square all of our x scores and then add them up, right? So we sum all of our x scores, and looks like the column here got squished, but we sum up, we square all of our x scores, and then we sum them up, and there you go. It's 6,012,400. That's a long number in there. Okay, and then we have only one term left to find, and that's the sum of x squared. And the sum of x we already calculated, right? Sum of x is right there, 5,380. So we just square that. Bam. My little box window there's cutting it off, but it's 28,944,400. Okay, so 28944,400. Just in case you're following along with the pen and paper. Okay, so let's take all of these values and get my head out of the way there, and let's plug and chug these things to find out what our slope is, to find out our b value. So all we do is start reducing this stuff. Pretty easy, right? There are all of our scores. Bam, bam. Let's start reducing. We end up with a B, or slope, of 0.00203. And we could just round that to 0.002. Okay? So that is how we would find the slope of our regression line. So that's our raw score coefficient, regression coefficient, or the slope of our line, 0.002. Okay, so the conceptual formula to find B, we ain't gonna worry about this. So forget that slide. But now that we have calculated B, we could easily find A, right? Because we needed our slope in order to find our y-intercept, which is A, but the formula is the mean of y scores minus slope times the mean of our x scores. So we already have that information. We calculated that previously. The mean of y is 3.36. Our slope, we just calculated that, 0.002, and the mean of our x scores was 1076. So we just plug and chug, and we end up with a y-intercept of 1.21, right? Okay, so remember we have a n of 5, a sum of x, sum of y, and the mean of 0.002. You can define this a value here. You simply divide find the sum of x. You just take find the mean of y. You would just take the sum of y divided by n, right? We know how to calculate the means at this point. So that's where 3.36 comes from. In our previous calculation, we calculated the sum of x, which is 5,380. We would divide that by n, or 5, in order to get a mean of x of 1076, right? So that's where this value comes from up there. Okay, so we could go ahead and start making predictions. How do you do that, you say, Brown? Well, we found our A value, right? We have an A of 1.21. We calculated that, right? Let's go back really quick. See? Right here. Once we found B, we plugged it in. We got a y-intercept of 1.21. So there it is. We just plop it in. So a predicted y score is is A plus B times X, right? Or our y-intercept plus slope times X. Well, there's A, and we calculated B before. We found it to be 0.002. So we're able to use this line to make, or this model to make predictions. So let's say a student has an SAT score of 1140. What would her predicted GPA be? Well, she has an SAT score of 1140. All we have to do is plop in 1140 where that X is, and whatever we get out is going to be the predicted GPA. Okay, so there you go. X, we plop in 1140, and we get a predicted GPA for this student of 3.49. Pretty good, right? Good for her. We don't know if that's a good prediction or not, right? But that's what our model says. This is the result that we get. This is our predicted result. So let's take an actual z-score, or an actual predictor, an actual X score. In this case, an SAT score of 820 from our previous example. So we'll take 820 out of our database, we'll plug it into this model and see how well or how close it gets to its corresponding GPA. And in our model, or in our data set rather, an SAT score of 820, that person had a GPA of 2.8. So let's see what happens when we put in 820 into our regression model here. Let's see what the predicted value is. We know the actual value for GPA is 2.8, but let's see what our model's predicted value is going to be. And that'll give us an idea of whether our model here is making good predictions or not. So all I did was plop in, remember this is our regression model based on that data. All I did was put in that student's SAT score, where X is, and I get a predicted Y of 2.85. Their actual Y score was a 2.8. So my model says that person, someone with the SAT of an 820, they'll have a GPA of 2.85. Their actual Y score was a 2.8. Their predicted Y score based on my regression model was a 2.85. Not bad, right? Pretty close. Pretty decent prediction in that regard. Okay, so let's use our regression line to see how well it predicts all of those actual Y variables. So this is the initial data set that we started with. So these are actual X scores and actual Y scores. There's no prime or hat on this Y. They're not predicted scores, but we're going to calculate predicted scores, right? So that's what this column is going to be. We're going to have the actual GPA associated with each of these SAT scores. Then we're going to use our regression line to calculate some predicted GPA scores, and we'll see how close they are. We'll see how much they match up or don't match up, right? So we have our regression line, our regression model, it's often referred to, right there. Again, the predicted Y score is the y-intercept, or A, plus slope, or B, times the X value, the individual X value. So we're just going to use this formula and plug in each of our X values. So the first one, 1000, yields a predicted Y score, Y hat, of 3.21. So boom, we'll put it in the predicted column. Our next score, 820, we already did this one, right? But let's do it again. We get a 2.85 as a predicted score. A SAT score of 1200 will yield a predicted score of 3.61. So we put that in the predicted column. A 1420, their actual GPA was a 4, perfect. So let's see how they do. Our model says 4.05, right? So we'll put that in the predicted column. And then finally, our SAT score of 940. Their actual GPA was a 3. Let's see what the predicted GPA is. 3.09. Okay, so we could take a look now at our actual scores, right? These actual Y scores and the predicted Y scores here. And just by eyeballing them, it looks pretty good, right? It looks like for such a small data set, there's only 5 pairs of scores that we're making these predictions on. And the predicted scores are pretty darn close to the actual scores here. So what we can do is actually graph this regression line. We could actually graph the line of best fit. Instead of just eyeballing it, we could graph it for real this time by graphing the X scores and the predicted Y scores. So the pairs of X and predicted Y. So let's go ahead and do that and see what our line actually looks like. So we have our X variables and we have our Y variable here. So the first score here is 1000 for SAT scores and a GPA of 3.21 is the predicted GPA. The next one, 820 on the SAT, predicted value of 2.85. And we'll just go down the line. 1200 and a predicted score of GPA, predicted GPA of 3.61, so on and so forth, right? Our last score there. Okay, so we can draw now a line of best fit through these scores. This is our regression line. Okay, so let's take a look in terms of the error that exists in this regression line, because just going back here, it's not perfect, right? Some of the scores it's doing a much better job. This one's a little bit more off. Then say this one is really close. That one's a little bit off. So it's doing a better job at predicting some scores than other scores, right? And that makes sense. Some of these scores are going to be closer to the regression line or the line of best fit, and some scores are going to be further away. This is what we mean when we talk about error that exists in our model. So in nearly every circumstance, our predicted Y scores are going to deviate from their actual Y scores. And that's okay. We refer to this deviation in actual scores and predicted scores as error, and all models are going to have some error. We want to keep it low though, right? So the amount of error that our regression model has depends on the strength of the relationship between X and Y. So the stronger the relationship or correlation between our X variable and our Y variable, the less error we're going to have. So the stronger the correlation, the less error we're going to have in making predictions. The weaker the relationship we have, the more error we're likely to experience when making predictions. Okay, so because the regression model represents the line of best fit, predictions for some participants are going to be closer to their actual Y scores than others. It's not the line of perfect fit, right? So it's the line of best fit. It's the best that we can do. And it'll do a better job for some pairs of scores than for other pairs of scores. So to describe the error in a regression model, we calculate something that's known as the average error across all predictions. And this calculation is very similar to computing a standard deviation. So let's take a look in terms of, say, how this actually works. We can, let's say, when it comes to evaluating strong and weak relationships, we hopefully know this by now, right? That the scatter plot on the left here represents a stronger relationship, and hopefully we could tell that just by looking at it, compared to, say, the scatter plot on the right, which has a weaker relationship. The scores are more spread out. There's a lot more variance here. In this model, the scores are hanging closer together, more tightly together. Not 100%, right? There's still some variance in there, but they're closer. So let's say if we had just one line to represent all of the data in there, the line of best fit, right? We would have lower error in this stronger relationship, because if we take a look at each of these data points and how far away they are from the line of best fit, remember the line of best fit says ideally in a perfect world all your data is going to line up on this one line, right? Because this is the line of best fit. So the closer your data is to this line, the better off all of us are. So we see that there's definitely error in this model, because the lines are not, or the dots are not lining up perfectly on this line of best fit. But let's compare, say, the deviation that exists. Each one of these arrows here represents a deviation of where the actual score is and where the line of best fit predicted the score would be, right? So the predicted scores would all line up on this line, but these are actual scores, so they're off a little bit. But if we go over to the scatter plot with the weaker correlation, or the weaker relationship there, take a look at those error lines or those deviations. They're higher, right? The line of best fit says all of the data here should be lining up on this line, but we can see much greater distances between the actual scores and the predicted scores. So the predicted scores should be on this line of best fit. The actual scores in a scatter plot, or in a distribution of scores that has, or pair of scores that has more error in it, or let's say correlation, a weaker correlation is going to produce more error in your prediction, in your regression, whereas a stronger correlation is going to produce less error in your regression. Okay, so just reading off the bottom here, some of it's getting cut off, but it says the error for any particular participant is the vertical distance between the dot for his or her actual score, right? These actual dots, or these dots represent actual scores, and the regression line, right? So the error for any particular participant is going to be represented by how far away their score is from this line. So even here, you could see that this person, there's less error. The regression line is doing a better job predicting this person than, say, this person, right? This person's actual score is further away from their predicted score, which would fall right on this line. But as a whole, this scatter plot, this correlation here is resulting in a lot less error than, say, this correlation here, right? The scatter plot, which represents a weaker correlation. We have much more deviation that exists between actual scores and their predicted scores down there. Okay, so when we talk about error in prediction, remember that we must first calculate variance in order to get standard deviation. So this is going back to like probably week 2 or 3 of 221. But let's take a look at our data as an example here. So going back to the data that we calculated, we have our calculated predicted y scores, y hat scores, and we have our actual y scores and our actual x scores, right? But we calculated these. These are the predicted scores. Okay, so using the formula for variance, we're able to calculate how much of a difference exists between our predicted scores and our actual scores, right? What we're really interested in is the standard deviation that exists between our actual scores and predicted scores, but we have to calculate variance first before we can calculate the standard deviation. So remember the formula here, the sum of squares divided by the degrees of freedom. So in this case, we're going to create a new column where we're going to subtract each of our, we're going to take our y-scores, our actual y-scores, and subtract out our predicted y-scores. So let's start by doing that, right? So there you go. I did them for you. We took all of the y-scores, we subtracted out all of the y-hat or y-predicted scores, and we have those values. Now remember, if we try to add these up to get a mean, to get an average deviation, we're going to end up with a 0 here, right? So this is why we have to square these scores first. So we have another column where we're going to square these scores. And we only do this because if we try to add them up, they're going to cancel each other out. So it's not gonna work for us here. Okay, so we square all of these scores, right? And we add them up, and this is the sum of squares. That's this first term right here of this equation. So next, all we have to do is divide by our degrees of freedom. We have 5 pairs of scores. Degrees of freedom is n minus 1. So we divide the sum of squares of 0.03 by 4, and we end up with a value of 0.008. So what does this mean? Well, essentially, let's just think about what we did here. We calculated the standard deviation for our error scores. What we did was basically find out on average how much error is there in the model, right? For any given predicted score, on average, how wrong is it going to be, or how much deviation will there be from the actual y-score, right? So for any predicted y-score we make, how far off is it on average from the actual y-score? That's what we just calculated here. So again, I'm blocking some of this off, but the variance of y-scores around the predicted y is the average squared difference between the actual y-scores and their corresponding predicted y-scores. So in other words, we take a look at how much deviation exists between our actual y-scores and the predicted y-scores, and essentially we get an average deviation, or an average error, essentially, right? So to calculate the standard error, remember this value here is variance. We have to unsquare everything. We have to, remember, we only squared this stuff to avoid getting a 0. We have to unsquare it now in order to get the value that we actually want, the standard deviation. So to calculate standard error of the estimate, we just take the square root of that variance term. So that variance term we said was 0.008. To find the standard error, essentially the standard deviation of our error, we just get the square root, right? So we take the square root and we end up with 0.089. Or to be conservative, we round up and say 0.09, right? So what does this mean again? The standard error says, overall, my predicted y-score on average is going to be 0.09 is going to be 0.09 points off from the actual value, right? So again, the standard error is giving you an overall term. Sometimes the actual y-score and the predicted y-score are going to have really little error, maybe no error, maybe they're exactly the same. For some scores there might be a little bit more error. What this is saying is, on average, how much deviation exists between the actual y-score and the predicted y-score. So the standard error of the estimate is similar to the standard deviation of the y-scores around their predicted y-scores. So we can kind of interpret this much the same way. It gives us an idea of how much error overall exists within our model. So it's basically the easiest way to describe the average error when predicting y-scores is the standard error of the estimate. Again, we'll be taking a look at all of this stuff in SPSS when we run these models in SPSS. So in our example, we had the standard error of 0.09. So when using our regression model to predict college GPA from SAT scores, when we are wrong, when our y-score is not the same as our predicted y-score, we will be wrong by an average of 0.09 GPA points. So not a whole lot of error there. We're doing pretty well in terms of error rate. The regression line does a pretty good job at predicting GPA scores from SAT scores, at least in our model here. Okay, let's hold off on this for a moment. We'll come back to this in the next lecture. Let's touch here quickly on multiple regression. So basically, so far we've only been using one predictor and one x variable to predict a criterion variable. We've been using SAT scores to predict GPA. But let's say if we had more than one predictor variable. Let's say we had SAT scores and we had high school GPA, and we want to see what happens when we include those two variables. What kind of predicted college GPA do we get, right? So, or in this example here, might as well use the example I got in front of me so I don't have to reinvent the wheel. Say we wanted to use more than one predictive variable. For example, several different variables such as stress, drug and alcohol abuse, heredity, etc. Might be useful in predicting, let's say, depression scores. So using more than just one of these predictors should theoretically help in making a more accurate prediction, right? So the more predictors, the more information we include in the model, the more accurate our model should be, in theory at least. So multiple regression allows us to predict someone's predicted y-score, in this case their depression score, by simultaneously considering his or her scores on all the predictor variables that we enter. So however many predictor variables we enter, we throw them into the model and we get a predicted y-score. So the hand calculations for multiple regression can get a little complicated. So we will learn, again in a different lesson, how to perform multiple regression using SPSS. But let's just take a look at what a multiple regression equation looks like, just so you can understand what exactly is going on in that to produce that SPSS output here. Multiple regression can be used or can be performed using z-scores, just like we did before, using z-scores to make predictions. And in this case, a predicted standardized y-score would involve taking a predicted standardized z-score on your first predictor, multiplying it by a standardized regression weight, adding that to the standardized score on your second predictor, multiplying that one by its standardized coefficient or regression coefficient, so on and so forth for each of your predictors, then adding them all up. If we're using y-scores, or raw scores rather, our predicted y value is again our constant, our y-intercept of a. That will never change. But each one of our predictor variables is going to have its own b, or value, or its own slope associated with it. So you would have to calculate your b value or your slope for each one of these predictors. And let's say the first one is stress. Our first predictor is stress. So once we have our slope for our first variable figured out, we plug in a person's stress score, multiply it by their the coefficient or the slope b. Let's say we have a heredity score. We plug that in, multiply it by its slope or its raw score coefficient, so on and so forth, and then we add them up. So multiple regression is just an extension of what we've been doing, but in this case, each predictor is going to have its own. For raw score, it's going to have its own slope. For standardized, when we're doing it standardized, they're each going to have their own standardized regression coefficients. So let's take a look at a z-score regression equation. Again, what we saw in the last slide, predicted z, standardized y. Here's our predictors, standardized scores for our predictors multiplied by their associated regression coefficients, right? So this is our, excuse me here, people calling me. These are our predicted z-score for y. We have a standardized regression coefficient for predictor 1. That's where x1 comes from. This is the z-score for our first predictor, x1. Then we'll add that to our this other little calculation we have to do. Beta 2 is the standardized regression coefficient for our second predictor, x2, right? And this z of x2 is the z-score for, or the standardized score for our second predictor, so on and so forth. Okay, so if you go through these slides by yourself, hopefully you can take a look at what's going on. You could have an unlimited number of predictors here. Once you start adding too many predictors, your model could get a little difficult to interpret. But remember that in bivariate correlation, when we're dealing with correlation between two variables, x and y, this beta value, this standardized regression coefficient, is equal to r. It's just the correlation between, so this beta 1, that value is just the correlation between x and z, right? Or not x and y, or x1 and y rather. The beta 2, the standardized regression coefficient here, is simply the correlation between x2 predictor number 2, and y, right? And so on and so forth. So there's an advantage in terms of using standardized coefficients. You just interpret those as correlations. They're easy to interpret. So again, in multiple regression, we must take into account the correlations between the predictor variables. So this is where the idea of multicollinearity comes into play. What if, say, predictor 1 and predictor 2 are really strongly correlated? Well, you're not going to end up with a good model, a good regression model. So we're going to let SPSS deal with that in terms of taking into account the correlation that exists between each of these variables, but that is something that we must take into account when conducting multiple correlation. Multiple correlation in terms of raw score prediction, we still have a predicted y-score right there. We still have our y-intercept, or a, or constant. That's not going to change. B1 is just our unstandardized regression coefficient for x1, for our first predictor. It's just the slope. It's just the slope for our first predictor, right? x1 is just our raw score for our first predictor variable, and the same goes for any other predictors that we add into the model. Okay, so multiple regression takes on the same, say, the same format as what we've been doing in terms of just using one predictor. In this case, we're using multiple predictors. Each one is going to have its own either standardized regression coefficient if we're using z-scores, or its unstandardized regression coefficient or slope if we're using raw scores. So some similarities between bivariate and multiple correlation. Both correlation and regression must involve a continuous y variable or a continuous criterion variable. Both can be done either with raw scores or z-scores, right? Also, the squared correlation coefficient is the proportion of variance that's accounted for. So remember, with bivariate correlation or Pearson's product moment correlation, R squared is the coefficient of determination. It lets us know how much of the variance or changes in one variable can be accounted for by the changes in another variable, right? So the same is true in multiple regression. So when we're dealing with z-scores, so when we're dealing with standardized scores, those beta weights in correlation or in regression, those standardized regression coefficients, if you square them, it tells you how much of your predictor is accounting for changes or differences in your criterion variable or your y variable. Okay, so the principle of this coefficient of determination, understanding how much one variable accounts for the other variable, or changes in one variable is accounted for by changes in the other variable, that applies to regression, multiple regression as well. Some important differences in here. In bivariate regression, you can only have one predictor variable, right? So that's what we started off doing. As an example, you can only throw in one predictor, one x value, and try to figure out a y score, a predicted y score. That should say number 2, not number 1 there. Also, in bivariate regression, beta equals r. However, in multiple regression, beta does not necessarily equal R. Excuse me, this is because in multiple regression, it takes into account the predictive value of the other variables in the equation. So what this means is that your beta value for each of your predictors, if you're using multiple regression, and I put in, let's say for GPA, I put in just one variable, SAT scores, and I get a beta coefficient of 0.8. Okay, that doesn't, if I square that, that doesn't necessarily mean, well, in that case, yeah, I could square that and say, you know, this proportion of my y-scores is being accounted for by my GPA. But if I throw in another variable, SAT scores and high school GPA, well, high school GPA and your SAT scores are going to be correlated as well, right? And your high school GPA and your college GPA are going to be correlated. So we have to take that correlation into account. Like I said, we let the computer deal with that. We don't deal with it. But it's something that we have to take into consideration, is that once you start adding more than one predictor, those standardized beta, or those standardized coefficients, those beta weights, don't necessarily equal R anymore. Okay, we can kind of interpret them as such, but they're not going to be exactly the same as if you just used one predictor in there. Okay, and finally, in multiple regression, the correlation between the criterion variable, your predicted y variable, and all the predictor variables taken together is called the multiple correlation coefficient, and it's symbolized by a capital R. Hang on to that term, because we're gonna look at it, and I'll explain it in much better detail when we do this in SPSS. But each model is going to give you a big R value, and that's the multiple correlation coefficient. However, because there's typically overlap between the different predictor variables, R, that big R, is usually less than the sum of the individual R's. So you can't just add up all your betas and say, okay, that's going to equal the big R for the model. That's not necessarily going to be the case. But each model, when we run multiple regression in SPSS, is going to give you this multiple correlation coefficient, capital R, that says all of your variables together is explaining this much of your y-scores. So it's telling you how much of your criterion variable is predicted by all of your variables taken together. Okay, I know that's a lot to take in. That'll be step 1 of understanding how regression works. Step 2 is reading the book, or the readings that I'll post. Step 3 will be the second video that I post, where we do this in SPSS. Step 4 will be the assignment that you do, and step 5 will be the synchronous live session, where we'll actually do this together as a group in SPSS in real time. Okay, so hopefully you watch this all through the end. You might not understand most of what the hell I said, but the second, third, fourth time you hear it is when things typically start to click. Okay, I will see you all soon, again, shortly. Have a good night for now.